Welcome back, everyone. My name is Pedram, and this is where we do machine learning codes and concepts. Let's get started. All right, this is our module number 4, machine learning fundamentals. So in this module, we're going to dive deep into the fundamental concepts of machine learning, which is going to serve as a foundation for the entire course. So I want you to pay very good attention in this module. If you remember, in Module 3, we covered linear regression models, but we talked about it from the econometrics approach. But from now on, we're going to focus on the models from the machine learning approach. So as you can see in Module 5, we're going to revisit this linear regression, but then we're going to talk about the machine learning approach. So I'm going to cover everything you need to understand what do we mean by machine learning approach, right? So here we're going to cover all the fundamentals that you need. Okay, we're going to do this module in 2 parts. In part 1, we will cover some basic concepts, and in part 2, we will answer this very important questions: how do machines actually learn? So what is this learning process, right? And I'm going to start with inference versus prediction. And as you can see, let me actually pull it up. Yeah. So if you remember from our module number 3, we talked about linear regression econometric approach. And there we said that we mainly use econometric in this world when inference is more important than prediction. But don't get me wrong, it doesn't mean that you cannot use econometrics for prediction. Of course you can. Once you have a model, once you have estimated the coefficients using, for example, an engine like OLS, then you can go ahead and use that model for prediction. But the point is that usually econometric models, we try to keep them simple, and that simplicity is going to help us to interpret things better, right? But at the same time, it comes with a cost that the prediction power is less because the model is not complex. On the other hand, this is where we are doing things in machine learning. So the main goal of machine learning is to come up with the better predictors. We don't necessarily pay too much attention to the inference, to the causal relationship between random variables in machine learning. So that's why prediction is mostly important in machine learning compared to inference. Again, this also doesn't mean that you cannot use machine learning for inference. There are some machine learning models that are simpler, like linear regression, that we can still use them for inference as well. So at a very high level, I want you to get a difference between machine learning world, which prediction is mostly dominated, versus the econometric world or statistical learning world, where the basically causal inference is mostly dominated. So step 1, what is the machine learning model? Okay, now let's see, why do we need a model? Basically, you want to see how we can quantify the pattern in the data, or in other terms, how the machine will be able to learn from the data. For that, we need to have a model. Now let's see what are the ingredients for that model, for that machine learning model, right? So imagine we come up with a functional form like this, and for now, we're not going to specify any constraints on that functional form. It says that our y is a function of x and theta plus some epsilon. So why we need to add some errors? Because we know that there is no true model out there and the data comes with noise. So for that reason, we need to have an epsilon in the model as well, right? So the left-hand side variable, or y, it's our response variable or dependent variable. Or basically, this is our output. In machine learning language, we call it the target. The x's are the predictors or the independent variables, and it's a vector of many features, right? We call them inputs, or machine learning algorithm. In machine learning language, we call them features. And then finally, thetas are the estimates or specification or the parameters of the model. Later on, we're going to talk about hyperparameters as well, but we don't necessarily show it here. Okay. So let's see, in a supervised learning models, what are we talking about? Remember, if this is my supervised model, then I have some inputs. It's a vector of features, and we have outputs as well. So both the inputs and outputs are given. And the machine is going to learn the pattern by quantifying this f of x, right? F of x and theta, you can think. So it's all about estimating that f, that unobserved relationship between variables, unobserved pattern between variables by f hat, right? So basically, the machine is going to learn by estimating this f hat, right? And it's going to do that for 2 purposes. One, we do this estimation to make some inferences, right? Basically, this is the interpretable part of machine learning. We want to become a storyteller. We want to quantify the relationship with variables themselves. And another reason is to make some predictions. We need to have f hat to, at the end of the day, be able to make predictions for a new set of data that the model has not seen before. So in machine learning application, and machine learning, basically we are focusing more than 90% of times on this predictability part, right? If you watch part 1 of these lecture videos, you will see that we talk about the difference between machine learning versus statistical learning. But this doesn't mean that we cannot use machine learning for interpretation, right? So if you use less complex models, we can come up with interpretable machine learning, and then we can use basically machine learning for interpretation. But as I said before, it is mostly used for making predictions. Okay, what are the parameters and hyperparameters? Let me give you a very simple example that you should be familiar with, and then we can see what are the parameters and hyperparameters. Imagine I'm regressing y, and I'm using a very simple polynomial regression model, right? So there's a constant plus theta 1 x plus theta 2 x squared plus, let's say, theta d x to the power of d, and of course adding some noise. Okay, what are the parameters in this model? The parameters are the thetas. So I have theta 0, theta 1, and etc. So these are the parameters, param. What is the hyperparameter? In this specific model, the degree of polynomial is going to be my hyperparameter. Does all the models, all the machine learning models have hyperparameter? No, right? So but this specific one has. For those models that have hyperparameters, just be aware that this number is going to be initially set by the user itself manually, and then down the road it's going to be optimized. So the parameters are estimated from the data automatically. By automatically, I mean by doing an optimization, right? And model hyperparameters are set manually prior to training the model. So this means that when we say an algorithm learned the pattern, it means it calculated the parameters, right? So model training happens when the parameters are solved for. So here we get the best model parameters. Let's show them with theta star. And then down in the process, we are going to tune the hyperparameters, the ones that we start with initial number. So let's say I started with d is equal to 4, and then we trained the model, the thetas were learned, and then when it comes to testing the model, during that process, we call it cross-validation. By using cross-validation, we're going to optimize the hyperparameters themselves. But these are some topics that we're going to cover in the future parts. For now, just remember, when the model is training using a train set, the thetas are going to be optimal. And after that, we are going to optimize the hyperparameters themselves and figure out what is the best number, in this example, for the polynomial degree. Okay. Now let's talk about parametric versus non-parametric models, right? Remember, the true relationship, that unobservable f of x, is unknown. And the goal is to see which machine learning algorithm is better at approximating that unobservable function, right? That f of x. An algorithm is going to learn or estimate that f of x from the training data. So basically it's going to figure out what is f hat of x, or we can add f hat of x and theta. And basically by training we mean the theta stars has been cleared, right? Okay, now let's see what is the difference between parametric model and non-parametric model and how we define them actually. So when this f of x that you're trying to estimate, if you impose some restrictions on it, if you make some assumption about a functional form, we call that model parametric, right? So in a parametric model, f of x is assumed. So what are the advantages of doing that? So it's going to be simpler, right? It's easier to understand and interpret. This is important. If you wanted to have an interpretable model, then you may better use parametric model. Not all the parametric models are interpretable though, but it's a lot more interpretable than the non-parametric model. It is going to be faster, basically because there's a functional form. So sometimes there's a closed form solution for the optimization, and the algorithm is going to go over to figure out what are the answers a lot faster. And for that, it's going to require less data, right? So these are the advantages. What is the disadvantage of parametric models? Basically, they're limited complexity. Because we are imposing some some restrictions, we are imposing some specific form, the parametric algorithms are basically more suited for simple problems where you can guess or you have some prior belief that what's the structure in the data. What are the examples of parametric models? We can think of linear regression, GLM, or logistic regression, simple neural networks, and some other models that down the road we're going to explore all of them. These are kind of parametric models, right? And parametric does not necessarily mean that there are parameters or not hyperparameters. It has something to do with that functional form that you're making an assumption about, okay? So non-parametric models, and as you can guess, if f of x is not assumed, basically if you're not imposing any restrictions on the functional form of f of x, then we call it non-parametric, okay? This basically means that the model is free to learn any functional form, right? So the examples are, for example, k-nearest neighbors, classification and regression trees, random forest, SVMs, artificial neural networks, and etc. These are the examples of the non-parametric algorithms. So what are the advantages? Well, as you can guess, flexibility. It can fit a large number of functional forms, so which doesn't need to be assumed. So these models tend to be more flexible. And for that reason, they're going to perform better, not necessarily, but on average, they usually perform better than parametric model because they're more flexible. And at the same time, this comes at a cost. What are the costs? It's going to be slower because there is no closed form solution for these models. So we have to use some gradient descent optimizers, solvers, and their families maybe. And for that reason, we require more data, and it's going to be slower. The learning process is going to be slower because we're dealing with more data. And these non-parametric models tends to overfit compared to parametric models, right? So they overfit more than non-parametric models, simply because the model is complex, it's more flexible, and if you don't control for the overfitting, they can simply overfit to the trained data. All right. Now you know what we mean by machine learning model. So let's talk about the data itself. So in real world, usually we are working with one realization of the data, one sample. That sample can have thousands of, I don't know, records of observations, right? And the idea is that we want to use some techniques called resampling techniques to make sure that we are training a better models that at the same time is flexible and avoid overfitting. I know these terms are all new, but just bear with me, we're going to cover them all in the next section. So for now, we're going to talk about splitting the data into three sets: train set, validation set, and test set. Let's see what are they. What do we mean by partitioning of the data set? The data set is typically divided into three non-overlapping samples. So imagine this is our data set D, and we are going to divide it into three parts. And let's say this data set D has 100 observations, right? So the first part is going to be roughly about 60 observations, and we call it train set, right? And the train set is used to train the model. This is where the parameters are being learned. The parameters of the model are being learned. The second set is what we call validation set, right? And let's say this has 20 observations out of 100, so maybe 20%. This is a set which is used for validating and tuning the model. Basically, this is the part that the hyperparameters of the model are being optimized. And finally, there's something what we call the test set, and it's usually 20 to 30% of the data, but let's say in this example 20%, and is used for testing the model's ability to predict well on new data, right? Because, guys, remember, it is important to test the model on something that the model has not already seen, right? Because otherwise it's going to be cheating. If I test the model on the train set, there's no point of doing that because the model has already seen that part of the data. Also note that the training set and validation set are sometimes referred to as in-sample, and the test set is referred to out-of-sample set. Okay, so to be valid and useful, any supervised machine learning model must generalize. So this is a term. It must generalize well beyond the training data. We need to make sure that our model is performing well on something it hasn't seen before, right? And so as you can see, we need to divide the data into three parts, right? So this suggests that in machine learning, we need to have some basically large data sets. But what if we don't have that large data set? Let's see what can we do with that. So if the dataset is not large enough, we need to do something which is called resampling methods. One of the resampling methods is called cross-validation. You know, down the road in this course, I'll talk about different resampling methods as well. So for example, what is bootstrapping, what is the oversampling by doing some synthetic sampling, and etc. But right now, let's focus on cross-validation. So sometimes, as we said, we cannot afford to split the data into three parts because the algorithm may not learn anything from a small training data set, right? So let's see what I mean by that. Remember, the algorithm is going to learn the relationship between variables, basically the patterns in the data, uh, by going over the train set, right? So basically, if the train set is small, then the algorithm may not learn anything. It's going to have hard time pinning down the parameters of the model if the train set is small. From the other hand, having small validation set is also problematic because the algorithm cannot tune the hyperparameters properly. Remember, the hyperparameters are being tuned, being optimized in the validation set. So in this case, what is the solution? The solution is combining the training and validation set. Okay, so this is the basic idea. We're going to say that instead of dividing the data into three parts, you know, training, validation, and test, we're going to make it into two parts. And so first part is going to be the training set. The second part is going to be our test set, which is also referred to as holdout set, right? So this way, we are going to have a larger train set, and in that way, there's a hope that the model is being trained using a larger data set. And then after that, we're going to use cross-validation on the train set in order to do two things. First of all, by doing the cross-validation, we can tune the hyperparameters. And secondly, we use cross-validation to estimate the performance of the model in the test set. So we use cross-validation in order to estimate the performance of the model in test set as well. So the goal is to obtain additional information about a fitted model, right? For example, to provide estimates of the test set prediction error, or if it is regression of the test set's the MSE or RMSE. All right. Now, what is k-fold cross-validation? So remember, we're going to use the train set and apply cross-validation over the train set, right? So how do we do that? We're going to divide the train set into k roughly equal size and non-overlapping groups. So for example, here we are going to divide our train set into 5 folds. 1, 2, 3, 4, 5. Right? We leave out one fold, in this case here, and fit the model to the other remaining k-1 folds, right? Finally, we obtain the predictions for the left out fold. So this is our left out fold. So we're going to train the model using these 4 folds and test it here. Test it on something that the model has not seen before, right? On that kth fold. And report the performance in that fold. Okay. Then the performance can be anything, right? If it is regression, for example, it can be MSE, RMSE. If it is classification, it can be accuracy, a fun score, you know, the precision, recall, and you name it. And we're going to repeat this process k times over k iterations, right? So here, again, we divided the train data into 5-fold, and we repeat this process 5 times. So in the next time, we're going to take this one as our holdout set, and then train the model here, test it here. In iteration number 3, we're going to take this one as our holdout set, train the model here, and test it here, and etc., etc. At each fold, at each iteration, we're going to report the performance of the model. And finally, we're going to combine these performance by taking a simple average, for example. So here, k is equal to 5. We take the average of, let's say, 5 RMSE, and we call it, if it is, for example, if it is regression, we call it RMSE1, and etc. And this thing is going to be our RMSE cross-validated version. Okay, so we already talked about step number 3. We have to do this iteration k time. Okay, and so that was the idea of cross-validation. So basically, we use k-fold cross-validation to simulate the validation set, and at the same time estimating the performance of the model in the test set. So this is how beautifully cross-validation is able to do that. Okay, and so there's another terminology which is we refer to leave one out cross-validation, and it is the case when there is only one observations in each fold left out, right? So for example, if your sample has 100 observation, if your train set has 100 observation, you can iterate, go over it 100 times, and each time leave one of the observations out and report the performance of the model on that one observation. Okay, so train the model on the 99 observation and report the performance in that one observation, and repeat this process 100 times, and then take the average and say that this is a cross-validated performance metric. So just to summarize, remember guys, the cross-validation is always applied to train set, and it's used for validating the model, basically tuning the hyperparameters, make sure that the model is not overfitting, and also to get an estimate of the test set performance, of the model performance in a test set. In the k-fold cross-validation, we implicitly assume that the observations in those k-folds are independent from each other. But this is not necessarily the case with time series, right? So for time series, we have to do time series cross-validation, because with time series, we cannot simply shuffle the data. And we also need to make sure that we are avoiding the look-ahead bias, right? We need to make sure that by the time that we're making the predictions, the future data is not already available, so we are not cheating, okay? So let's look at different types of time series cross-validation, and these are the most commonly used ones. So one is walk forward cross-validation expanding windows, and the other is walk forward cross-validation rolling windows. Okay, so let's see what is the idea of expanding windows versus rolling windows, and where we should use each versus the other one. Okay, so starting with the expanding windows. So the idea is very simple, right? So imagine this is your data set, and this is our time axis, right? So basically we say that, okay, let's say here, use this part of the data set to train the model and test it on this part of the data set, right? Next, we're going to say that, okay, let's expand this train set. So we're going to take the entire thing here, call it train set, and test it here in the test set, and etc., etc. Next step, we're going to take all this part, we're going to expand the window. We call it train set and test it on the test set, right? So by doing this, we just need to make sure that we're not using this part of the data as train set, right? Because this is what we call avoid look ahead bias. We just need to make sure that by the time that we are making predictions, we're not using this information, which is not available at that time, okay? And so this was the idea of expanding windows, walk forward cross-validation using expanding windows. On the other hand, we have the idea of rolling windows. So what is rolling windows? This is our data, and we're going to say, okay, let's take this part of the data, train the model here, test it here, and then we're going to, let's say, this is the window, we're going to shift this window to the right? So this is our rolling window. We shift it. Instead of starting from the beginning of the data set, from the time series, we're going to start, let's say, keep time series rolling windows of, let's say, 60 days, right? So this is 60 days, for example, and you're rolling it forward. So 60 days, 60 days, 60 days, and etc., etc. Now, why do you think we should use, for example, rolling windows versus expanding windows? What do you think? Well, especially in financial time series, it's usually the case that uh, there's a structural change in the data, especially in the earlier part of the data. Imagine we are talking about a stock price, and let's say you're thinking of a company like Tesla, right? Back in the days, the growth was different. The company was in the growth was just in its initial steps, and then after a couple of years or after 5 years, there was a huge structural change in the behavior of the stock price of that company, right, or any kind of other growth company. So for those kind of time series, it doesn't make any sense to go from the beginning of the data sets to the very latest days of the data set, right? So it's going to be a better idea to roll that window over time. Let's look at the stock market price for every 60 days before, and then roll that window forward. Okay. Nowadays, there are more advanced time series cross-validation techniques available, and which I'm not going to talk about them here, but maybe in the future videos I will cover them. Basically, some techniques like purge k-fold cross-validation, which use the ideas of purging and embargoing, basically by removing the overlaps from train and test set and just making sure that those overlaps and data leakage is avoided. All right, next part, evaluation metrics. Now that we know what are the machine learning models and what are the ingredients, let's talk about how we can compare those models with each other, right? Basically, let's talk about evaluation metrics. In general, we want to compare how close are the predictions of a model to the actual numbers in the test set, in a set that the model has not seen before, okay? And here's a list of evaluation metrics for classification and regression. We're going to talk about the details of these terms down the road in future parts, but for now, you can just look at this laundry list of the performance metrics. So for example, in classification, we can report confusion metrics, and accuracy, precision, recall. We talk about F-score, AUC, ROC, log loss, Gini coefficients, and etc. And when it comes to regression, we can report, mean absolute error, mean squared error, root mean squared error, and etc. Okay. But as I said before, we're going to talk about the details of all these performance metrics down the road. But typically, in regression analysis, we're interested to report the MSE or RMSE. And for classification analysis, we will be reporting some rate for misclassification rate for quantitative responses, right? Okay. Now I want to talk about one of the most important concepts in machine learning. So this is going to be super important, so I want you to pay very good attention here. So the concept is bias variance trade-off, optimization versus generalization. So what do we mean by these terms? So a good machine learning model is a model that can generalize well. So this is a term that we use. So it means that we have trained a model using a train set, and that a model is a good one that can generalize well in the test set in something that it hasn't seen before. So this is what we call generalization. But at the same time, we want to make sure that our model is complex enough, it's flexible enough in the train set that can learn the complex pattern in the data. So this is called the optimization part. But there's a trade-off between the two. If you over-optimize the model, if you make it super complex, yes, it's going to perform absolutely fantastic in the train set, but it's not going to do good in the test set. So we say that the model is not generalizable, and this is an issue. So where's a good trade-off? What is a good balance between optimization and generalization? In order to answer that question, we need to understand what is the concept of bias and variance. So let's cover them. Okay, now what is model bias and model variance in machine learning? Remember, when we talk about bias and variance, these are the properties of repeated sampling and not just one realization of the data, right? So we have to be careful that we are dealing with repeated sampling, okay? Now let's start with a very simple example. Imagine this is our target variable and this is our only one feature in the data set. And the black line is the unobserved true relationship between the observation and the data, right? Our machine learning model is expected to estimate, to learn this pattern in the data. And imagine the pattern is just this simple curved line, right? The black curved line. The machine learning model is expected to learn this pattern, okay? Now, imagine the first model that we're going to use is a very simple linear regression model, and it's actually the most simple form. You know, we think of the, let's say, the average, right? So this is going to be our model, right? So this is our very basic model, this line. Now, I want you to think about what happens to this model, what happens to its variance, and on average how it's capturing the pattern if we change the sample, right? If you work with another sample. Now, if I simply use another set of data set, let's say the red ones, right? And the model is the same, so the new fit is going to be, maybe this is going to be just a slightly different, right? Maybe this is going to be the new fit. And as you can see, on average, I'm talking about average of these lines. On average, the model is off. It's not capturing the true pattern. Remember, the black one is a true pattern. And on average, we are not capturing that. So this concept is what we call bias. So in this simple example, bias is going to be very high because on average, we are not capturing the pattern. Okay, but what can we talk about the variance? I want you to think about this blue line and red line. So these are only two realization of the data. What if you're repeating this process thousands of times? So the variance is going to be very small, right? Because as you can see, for every realization, the model is super simple. And for that reason, it's not capturing the let's say, the average pattern in the data. And the variance is going to be also very small, right? So in this example, we showed that if the model is very simple, the model bias is going to be high and model variance is going to be small. Okay. Now let's look at another example. Now let's focus on very complex model, right? So in the previous slide, look at the very simple example, simple machine learning model, and we saw that the bias is very high because on average it's not capturing the pattern and the variance was small. Now let's focus on a very complex model, and by complex model, for example, you can think of a polynomial regression model with very high degree of polynomial, right? It's super flexible. Basically, it's capturing unnecessary noises in the data as well, right? So let's exaggerate a little bit and say that this model is super complex. So if the model is complex, what is it doing? So it's going to do something like this, right? Maybe for this realization, the model is going to capture everything, right? It's going to perform a very good job in terms of fitting the data, right? And now let's look at another realization. So here is another realization of the data, and the model is going to do something like this because the model is super complex, right? Now I want you to focus on these two lines, right? The green one and the red ones. And remember, the model is super complex. So what can you tell about the variance of the model? As you can see, the variance of the model is going to be very high, right? Because if you look at the model fit for different realization of the data set, we see that the variance there is going to fluctuate a lot. Compare the green curve between and the red curve, right? So the model variance is going to be high. But what about the model bias? So what can we say about the model bias? Model bias. Remember, go back to the definition of model bias. On average, are we capturing the pattern in the data or not? On average. So it means that if I do thousands of auto realization, right? So maybe this is one, this is another one. Let me use another color. Maybe this blue one is another one. But as you can see, on average, it is capturing the true relationship between the data, which was that black f of x, right? So the model bias is going to be small because it's on average, it's capturing the true relationship, that nonlinear curve in the relationship in the data, right? So in this example, we show that if the machine learning model is super complex, the model variance is going to be very large, but the model bias is going to be small. So as you can see, there is a trade-off between bias and variance, and this is what we mean by the bias variance trade-off in machine learning. And again, I repeat myself, remember, bias and variance are the concepts of the properties of repeated sampling, not just one realization of the data. Okay, now let's see how we can quantify the bias variance trade-off by looking at MSE decomposition. So we can show that, we can mathematically show that, and this is actually what I'm going to show you in the next slide, that mean squared error is going to be consists of three parts: model variance, model bias, and irreducible part. Okay, so as we talked about it in last slide, model variance is the variance if we had estimated the model with a different training set, okay, or with a different data set, basically. Model bias is the error due to using an approximate model. If the model is too simple, we show that the model bias is going to be high. If on average we are capturing the pattern in the data or not. And the irreducible error part is basically due to some missing variables and some limited samplings, right? It cannot be fixed by modeling. So the goal is to minimize the sum of model variance and model bias. So the goal is to minimize the combination of the two, okay? Because remember, this part, the irreducible part, cannot be fixed with modeling. So if you want to make sure that the model variance and model bias are a combination of the two is the smallest, we have to, this concept is known as bias variance trade-off, because reducing one will lead to increasing the other one, right? We showed the visualization in the previous slides, right? When the model was super simple versus when the model was super complex. Okay. Choosing the flexibility of f hat of x, basically this is what the model is learning, the true pattern in the data, is going to lead to bias variance trade-off, right? So if your model is super simple, the bias is going to be high, variance is going to be small. If the model is super complex, the bias is going to be small and the variance is going to be large, right? So a best combination, of course, is going to be somewhere in between. Okay, now let's see if we can mathematically decompose this MSE, mean squared error. As we stated earlier, the bias variance trade-off is one of the core concepts in supervised learning, right? Assume that the data is generated by a very simple model, and this is our model. Our target variable is a function of x. It can be, we can add the parameters and hyperparameters as well, plus some noise. And this is a property of our noise, right? On average, there's 0, and the variance is constant. The estimated model will be something like this. Our y hat, these are the predicted values, is equal to f hat of x. So this is what the model is going to learn, right? And then we can decompose the mean squared error by writing this equation. So we are interested to see what is the expected value of epsilon hat squared. So this is our mean squared errors, right? And then by definition, it simply is as expected value of y minus y hat, or f hat of x to the power of 2. We can just, instead of y, we can replace the f of x plus epsilon. So this is our y, and then simply square it, okay? Then we can use the properties of expectation, and we already know that the expected value of epsilon is 0, so we can reduce this one into two parts: the irreducible part and total quadratic error, okay? Then we can use some properties of conditional expectation and open up this squared version, and after doing some simplification, we get to this two equations, right? We will see that this equation on the left hand side is a combination of variance of the model, variance of f hat of x, and bias squared, right? And remember, this expected value of f minus f hat is the definition of bias on average, if the model is capturing the pattern or not, right? How off we are from the true pattern in the data, plus that some irreducible part. Okay, so this was the mathematical version of the MSE decomposition. All right, now let's visualize the bias variance trade-off. Okay, so imagine, we already showed these things in the earlier slides, but let's quickly review them and put them together, the model bias and model variance, and see what is the optimal complexity level. Okay, So on the left, we have a very simple model, and we know that if the model is simple like this, the bias is going to be high, because on average we are not capturing a true pattern in the data, but the variance is going to be small, because if I look at different realization of the data, that flat line is not going to change a lot, right? On the other hand, if the model is super complex, we know that the variance is going to be high, because if I look at another variation of the data, it's going to be a lot different than the first one. However, on average, we are capturing the true relationship, right? So on average, the bias is going to be smaller. So as you can guess, a best combination is going to be somewhere in between, right? A model which is not super simple, or the model which is not very flexible, right? Then mathematically, how we can get to that point, right? So the idea is that we can plot the test error versus model complexity, right? So on the left, the model is super simple. On the very far end, the model is complex. And we are interested in to look at the performance metrics in the test error, right? Because guys, remember, we have to look at the metrics. For example, this is regression analysis. We can look at the RMSE or MSE itself in the test set, because we want to test the performance of the model on a data set that the model has not already seen, right? We don't want to cheat here. We want to make sure that we're reporting these numbers for the test set, okay? So if the model is simple, we are on the left side, and we already showed that when the model is simple, the bias is very high, right? So let me use blue. So the bias is going to be very high, and the variance is going to be very small, right? If you're on the far right hand, when the model is super complex, the bias is going to be small, because on average we are capturing the pattern. Remember, on average we are capturing the pattern. However, the bias is going to be very large, right? So if we add these two together, this is our total test set error, which let me actually use another color. So this is how it's going to look like, the combination of the two. Variance plus bias squared plus irreducible error. And as you can see, when the model is super simple, this is high, and when the model is complex, this is also high. So an optimal level of complexity is that, so if you start with a very simple model, we go to the right. If we start with a very complex model, we go to the left, and hopefully we will end up somewhere in between, right? Okay, so this is one representation of bias and variance trade-off, and there's another one which I'm going to show you on the next slide. Okay, here is another representation of the bias variance trade-off. So I can actually divide this quadrant like this. We have low bias versus high bias, and low variance versus high variance. Of course, ideal case, the best case scenario is going to be low bias and low variance right here. Look at that. On average, we are capturing the pattern, we're hitting at the target, and the variance is very small. Remember, this never happens. We cannot have the best of both work together, right? So this is ideal, which rarely happen. The worst case scenario is like this, that we have the bias is high, as you can see on average. So if I take the average of these black dots, maybe this here is the average. On average, we are off from this. Maybe from the center from the center here, and on average we are off, and the variance is also high. Look at that, black dots, right? Black circles. So this is very bad. This is a worst case. So ideally, we want to end up with somewhere that's there's a combination between bias and variance, right? So here on the lower left quadrant, the bias is high, but the variance is small. We can look at the black circles. So they're close to each other, so the variance is small, but the bias is high, because on average, if I calculate the average, this is going to be the average. On average, we are off, right? And on the so what is this model? Do you remember? So this is going to be an example of a simple model or a complex model. Yes, a simple model, right? When the model is super simple, the bias is going to be high, but the variance is going to be small. On the other hand, if the model is complex, we are here. When the model is complex, the bias is going to be small. What does it mean? If I take the average of these black circles, maybe I ended up here, which is very close to the yellow circle. So on average, we're hitting at a target, but the problem is that the variance is high. So if you look at the black circles, the variance is high. Okay, so this is a complex example of complex model, and this is a representation of bias variance trade-off, and we hope that, I don't know, maybe we end up somewhere here in between, wherever we get the minimum value for the our performance metrics in the test set. Okay, now let's talk about the concepts of overfitting in machine learning. Overfitting happens when the fit algorithm does not generalize well to new data. Basically, it means that if you use another realization of the data, the model is not going to do a good job. Let's look at a bunch of examples. So this is an example in regression analysis. So imagine we have our output variable on the y-axis. This is the output variable is going to be continuous, and on x-axis we have just one predictor, right? So the first model, and imagine this is the model that we're using, the dashed black line. And of course, the true relationship in the data is going to be something like this. Okay, so this black dashed line is going to be a very simple model. So if the model is simple, go back to the definition of bias variance trade-off, right? Model is simple, bias is going to be what? Yes, bias is going to be high and variance is going to be small. When the model is complex, bias is going to be small and variance is going to be high, and maybe this is a good combination. However, we are going to give this super complex model another name as well. So this is what we call overfitting. When the bias is small and variance is large, and this model is a very good example of overfitting model, right? Because it does not generalize well to another data set. If I use another data set, maybe by data set I mean another representation of the same population, right? So maybe use another train set, then I will get something like this, and well, I don't know, maybe something like this, and we know that even though on average we're hitting at a target, we're capturing the pattern, but the variance is large. So this is called overfitting. So that was a representation of overfitting in regression, and here is a representation of overfitting in classification, right? So this is classification example, and how do we know that? Because look at that, we have x1, let's say, and x2, and these shapes, cross versus circle, is basically our y level, right? So our target variable is categorical. In this case, two classes, a cross, green cross, and let's say these are brownish circles, right? Now again, and these red lines are our classifiers. So the red lines that we see are classifiers. We're going to talk about different classification models and regression models down the road, but the visualization, it should be very straightforward to follow. Okay, so in the first case, the model is underfitting because, as you can see, it's a very super simple model, and it's underfitting. It means that the bias is going to be large because on average it's not classifying the data properly, right? And on the very far right, we are overfitting. So this is an example of overfitting classifier. So even though the boundaries, the classifiers are doing a perfect job in this data set, if I use another representation of the data, this is going to be performing very badly, right? Because this complexity is going to comes at a cost for us, right? It's not going to be helpful down the road. It's a complex model, is overfitting the data, and it's not going to be generalizable to a new data, right? So let's summarize all these things in bullet points. So the model fits the training data too well when you're talking about the concepts of overfitting. And it's not predicting well in the new data, right? Not surprisingly. We also say that the model fits the noise in the training data. Find a pattern that does not exist. So for example, in this example, or in this one, maybe this is not the pattern. The pattern is something as simple as this. And the model is, that complex model is capturing something which does not exist. It's basically capturing the noise instead of the pattern in the data. Okay. And we also say that the algorithm is memorizing or has memorized the data rather than learning it, right? So when the model is complex, when the model is overfitting, we say that, okay, it seems that the model is just memorizing, the machine is memorizing the data instead of learning from it. It means that it cannot be generalizable to a new data set. Or simply we say that the model is too complex. I think we already looked at this concept multiple times so far. All right. All right. So we said that having a model that overfit is not necessarily bad. Actually, we want to have that model, right? But let's say we have that model. How can we fix this overfitting part? There are different ways to do that. The first and most common one is collecting more data. Okay. So for example, look at this. Let me use the right marker. Look at this data set here, right? We have 1, 2, 3, 4, 5 observations. If we have only these 5 observations, we can make the model complex and get this kind of pattern, right? However, if we collect more observations, which is going to fill the gap here, then we get to the next chart. This is a data set with more observation, and as you can see, the model is able to fit the data a lot better with a simpler model, right? So this is collecting more data. What I want you to be very careful is that collecting more data does not always work, and there's a reason for that, because what if your data that you're adding is simply just noisy and there's not much to learn from that data? So let me give you an example. Imagine you have, this is your error, and this is your model complexity. Okay, and you are doing, it seems you get something like this. No matter what you do, this is the performance of the model in the train set. Even in the train set, you cannot reduce the error as much as you want. So for example, this is your benchmark, or maybe lower than this. This is a benchmark, so this is benchmark error, and by no means you're getting close to that benchmark error, no matter how much you make this model complex. Guys, pay attention. This is a train set performance, right? Usually the train set performance should be something like this, right? But if you get something like this, it means that your data is not just getting it. The data is not informative in terms of explaining the target variable. So if that's the case, don't waste your time. Collecting more data is not going to help. So the next approach that we can combat this overfitting is what we just talked about, is right, some regularizations, complexity reduction. So for example, we go from this super polynomial model and we add some regularization terms. We are going to penalize this regression for having higher polynomial degrees, and it's going to make it to less complex by something like this, right? So these are different techniques. Again, one other techniques for complexity reduction is feature selection, basically engineering the features and come up with more informative features, hopefully to explain the target variable with simpler data. And then finally, we can always use our cross-validation and look at the performance in the cross-validation to come up with a better trade-off between bias and variance. So this is what we covered in the previous slide, right? So we use cross-validation, or in deep learning we do the validation set only sometimes, to figure out what is a better combination between the optimization versus generalization, between bias and variance, okay? All right, before we move on to the solvers and optimizers part, so let's talk about yet another curve that's going to help us to answer this question. Do we need to collect more data, right? So this is called learning curve, and it's very important. It's a very intuitive one. A learning curve is a plot that shows the relationship between the training set size from one hand and the performance of the model from the other hand, okay? It is basically used to diagnose that if your model is going to have a high bias, high variance, or it's just fine. It has the right combination of the two, right? So let me give you an example. Imagine, so this is a very important one. Pay attention because this is usually confusing for students to understand. So imagine this is your model. Okay, so your model is a very simple quadratic function. Let's say y is equal to, it's very simple, just x1, and this is your y. Y is equal to, let's say, some bias term plus w1 x1 plus w2 x1 squared. Very simple model with some noise, right? If this is the model.
Now I'm going to say, okay, this is the model. Now, if the train size is just, let's say this is the only train size, right? And that's your model is perfectly capturing that one if you only have two observations. So if you're here, let's say two observations, if I have two observations, the error is zero, right? Because the model is going through those points in the train set and it's doing a perfect job, right? However, not surprisingly, the performance, so this was the performance in the train set, the performance in the cross-validation set or in the test set, it's going to be way worse, right? Because maybe in the cross-validation, we had observations like this. And we know that this model is not capturing anything, right? So the performance in the cross-validation set when the observation number is small, it's going to be very, very bad. Okay. Now let's start increasing the number of observations, right? So let's say we add a bunch of more observations. We get something like this. Okay. And now as we increase the train size, of course, the performance of the model is going to get worse because now we have more information and the model needs to fit the more information. And I want you to focus on the blue ones here only. Let me erase this one. Just the model needs to focus on more information and maybe it's not necessarily doing a good job for these observations, right? So what it means that the error is going to increase. Your measure of performance in terms of error is going to increase as the train set size increase because it's going to have harder time to fit the model. But on the other hand, this error is going to decrease for the test set or for the cross validation, right? Because again, if this is a cross validation data, it's going to be a lot better than this because we have more information now. I'm sorry. So we get to a point that these two curves are going to converge, right? Now, now you have to look at the your benchmark performance, right? Or we also call it common sense performance. Imagine this is your benchmark performance. If your model is not able to predict well for large size in the train set, even for the train set, right? So if your model is not outbidding the benchmark performance even in the train set, it means that your model is suffering from a large bias. So the bias is high. No matter how many iterations you do, no matter how large the sample size is, on average, your model is not hitting at the target. You know what? Maybe the target was something like this. Maybe the model needs to be polynomial to the degree of 3, right? So that's where you figure out that, okay, this distance is high. It's not outbidding or it's not beating your benchmark performance, but they're converging to each other. So it means that you have a high bias problem. Okay, so that's a high bias problem. What is the high variance problem? High variance problem happens when the gap between this performance metrics between validation sets and train set is large and it remains large no matter how much you increase the train set size, right? So let me give you another example to make sure that you understand why this gap may remain large. So here we say, let's say our true model is good and actually it's, let's say, using the same observations from the previous example. Imagine we got the right model. It should be something like this, right? Y and X. But the problem is that this is your train observation. This is your maybe cross-validation observations. So maybe we get some observations here, right? So it seems that in cross-validated, the model is not capturing the performance well simply because we don't have enough observations, right? If we keep adding more observations, right, if we go to the right, these two curves should converge eventually. We should get to a point, something like this. So if the gap is large, this is a sign that your model has high variance, and we can fix it by collecting more information. Okay, so and when it is when you plot the learning curve, a just right model is, let me actually show it to you. So what is a just right model? So you have the cross-validation score that decrease relatively fast, and then the train score that increase relatively again fast. And for a decent amount of data, we are outbidding the benchmark as well. Hopefully, we're outbidding the benchmark as well. So this is a just right fit between bias and variance. Okay, so that was the learning curve.
All right, so I know it was a relatively long video going over all the machine learning fundamental concepts. Don't worry too much. I don't expect you to become an expert after this 60 minutes. The whole point is that having all these concepts in one place for you to use it as a reference. You can come back to this video, watch it again to make sure that you understand these things deeper when you're going over the machine learning models in general. Okay, so I'm going to leave you with this fun exercise, and I want you to think about this picture and see how we can relate it to the concept that we learned. Specifically, in order to give you a hint, think about the concept of optimization versus generalization. Until the next one, take care.